So far we have seen a charged particle moving in electric field or a charged particle moving in magnetic field alone. Now we will see when the charged particle moves in the region where both electric and magnetic fields are present. Suppose if a charged particle is moving, the force experienced by a charged particle moving in a region where both electric and magnetic fields are present is called a Lorentz force. See, electric field also should be there and magnetic field also will be there, and if the charge is moving with the velocity v in both this region, the force experienced by the charged particle is called Lorentz force. Lorentz force. So let us see for electric field. Electric field. Electric field E. The force experienced due to electric field is equal to Q into E. Q into E, and the direction of force. The direction of force is along the direction of electric field. Direction of electric field. Because this is a scalar, the direction of electric force on the charged particle is in the direction of electric field. Suppose this is positive and this is negative, this will be the electric field, and this will also same direction electric force due to electric field. This is for electric field alone. Now for magnetic field. For magnetic field B. If the charged particle is now moving in magnetic field, it will experience, the charge will experience a force, because the charge moving with velocity v, moving with velocity v, and the charge will experience for magnetic force is equal to charge into cross product of velocity vector and magnetic vector. This already we have seen. The magnetic force will be parallel to the vector v cross b vector, and magnetic force vector will be perpendicular to velocity vector, and magnetic force will be perpendicular to magnetic field vector. So this already we have seen it. The magnetic force experience, this force. See, we see this is the velocity vector, this is a magnetic field vector, and this is the angle between them. The force will be in this direction, which is also the direction of v cross b vector. So this already we seen, this is lying in the one plane. Okay, so this force is perpendicular to the plane containing v vector and b vector. This vector, this is Fm, is perpendicular to the plane containing v vector and b vector. This already we have seen it. Again I am repeating it. This force is perpendicular to the plane containing v and b, whose direction can be found out. So this direction of this force can be found out by Fleming's left hand rule or right hand palm rule. Right, left hand rule or right hand palm rule. Therefore total force on the charged particle. And the total force on the charged particle moving in the region of electric and magnetic field is the total force. This is, we call it as a Lorentz force. Total force is equal to force due to electric field plus force due to magnetic field. Force due to magnetic field, that is, which is equal to Q into E vector plus Q into V cross B vector, or we can take Q outside, E vector plus V cross B vector. This total force is called a Lorentz force. This we can write like this also. Q, we take Q, since Q is scalar, we can take outside, then E vector plus V cross producted with the B vector. This is the total force. So we can define the total force experienced by the charged particle moving in a region where both electric and magnetic fields are present is called Lorentz force. As we have found out, the force experienced by when a charged particle moving in a combined electric and magnetic field is given by E, this E plus V cross B, where rest of the things have its usual meaning. This stands for velocity of the particle, magnetic field, electric field vector, and charged particle. Now the condition, first when we say velocity vector, electric field vector and magnetic field vector are collinear. If it is collinear, means what? Either this is the velocity of the magnetic particle, this is the magnetic field and this is the velocity of the particle and this is the electric field. So first we will deal with the magnetic field. See, when a particle moving, collinear means what? Either it will be moving parallel or anti-parallel. It means this particle is moving parallel with the magnetic field, particle moving anti-parallel with the magnetic field. Moving parallel means the angle between this and this is theta is equal to 0, and when it is moving anti-parallel, this is moving in this direction, the particle is moving in this direction, which is equal to 180 degree. Since magnetic field due to magnetic field is equal to Q into V cross B, in magnitude form we can write Fm is equal to Q into velocity into magnetic field into sine of angle between these two vectors. Here theta, here what is theta? In this condition both are in same parallel, here both are anti-parallel. Either theta is equal to 0 and sine of theta 0 degree is equal to 0, also equal to sine of 180 degree. Whether it is sine of theta is equal to 0 degree or 180 degree, whose value is equal to 0, the net magnetic force is equal to 0 in this condition when velocity particle moving in a collinear. Collinear means it may, if this is the magnetic field direction, particle may move in this direction or it may move anti-parallel. In that condition, the theta angle between this, that is magnetic field and velocity, theta is equal to 0 degree, and this is magnetic field, it is moving then this is velocity vector, and in this case theta is equal to 180 degree. In both the cases force due to magnetic field is equal to 0. So it means what? But now what about the electric field? For electric field, Electric field does not have any angle factor. So electric force due to electric field is equal to Q into E. Whether it's moving anti-parallel or parallel, the electric force is along the electric field direction. Electric field direction. It means the electric field, see, we can say as a result there will be, so along the electric field, when the magnetic field, the force due to magnetic field is zero on the charged particle, and electric force on the charged particle, there will be a force, that is force due to electric field is equal to Q into E. There will be electric force. If there is a force, acceleration is equal to force by mass in vector form. If there is a force, acceleration will definitely be there. It means force is this one, therefore acceleration is equal to force vector divided by mass is equal to force is equal to Q into E vector divided by mass. In scalar form, acceleration is equal to Q into E divided by m. This is the acceleration produced. We can find out, it means when a particle moving collinear with the electric field and magnetic field, the magnetic force on the particle is zero, but due to electric field there will be acceleration which is given by A is equal to charge into electric field, magnitude of electric field divided by its mass along the direction of electric field. Along the direction of electric field. Along the direction of electric field. As a result, due to this result, what will happen? As a result, there will be change in speed because there is acceleration. Acceleration, what is acceleration? Acceleration is equal to V minus U by T. In vector form also we can write. If there is no change in initial final velocity, acceleration is equal to zero. If there is change, suppose initial velocity is U and final velocity V, there will be acceleration. There will be acceleration. If acceleration has to zero, both has to be equal. If both are equal, this minus this is equal to zero divided by T. Acceleration is equal to zero. So as a result, there will be a change in speed. Since there is an acceleration, since there is acceleration due to electric field alone, because in magnetic field, magnetic force is equal to zero. Magnetic force is equal to zero means acceleration is equal to zero due to magnetic field. As a result, there will be change in the speed of the particle. As a result, due to E, there will be a change in speed. Change in speed of the particle. How do you say speed of particle? How do you say there is a change in? If there is a change here, then only acceleration here. If there is no change, this denominator, that is A is equal to V vector minus U vector by T. This minus this should be non-zero, then only there will be acceleration. If both are equal, then acceleration is equal to zero. But there is an acceleration given by A is equal to QE by M. It means if there is an acceleration, there is a change in velocity and hence there is a change in the speed of the particle along the direction of electric field, along the direction of electric fields. But there will be, but what will not change? Speed will change, but there will be no change in the direction of motion. But there will be no change no change. See here, there will be change in the speed. Change in the speed, but there will be no change. There will be no change in the direction of motion. In the direction of motion. Because speed is changing, acceleration is there, due to which there will be a change in speed, but there will be no change in the direction of the motion of the charged particle. But speed, velocity, what else? Velocity and moment. One more thing related with velocity, momentum, and what else? Speed, velocity, momentum, and one more thing is the kinetic energy. Kinetic energy of the particle will change. Which will not change? Only thing, what thing is not changing? There will be change in the speed. There will be no change in the direction of motion. If it is moving in this direction, it will keep moving in this direction only. No change in direction of motion, but speed. Because since acceleration is there, what is the speed? Speed changes. Speed change. Okay. Velocity. This is once speed is changing, velocity will also change. Velocity change, kinetic energy, that is kinetic energy is equal to half m into velocity square. If this is changing, this will also change. Then momentum is equal to mass into velocity. In vector form we can write it. Here also we can write it vector form, velocity. If velocity is changing, momentum will also change. So we can conclude there will be no change in the direction of motion of the charged particle, but speed, velocity, momentum and kinetic energy of the charged particle will change. Here we have to note one thing, an electric charge always, charged particle will always experience a force in an electric field, whether it is stationary condition or in motion. That is, we can say a stationary charge. See, F is equal to magnetic force is equal to Q V B into sin theta. Stationary means stationary. That is, velocity is equal to 0. In that case, Fm is equal to 0. Now, F, electric field, is equal to Q into E. It has got nothing to do. For a stationary or moving charge, Q. If it is moving charge also, there will be, whether it is stationary or moving, because this angle factor is not there. So whether it is stationary or moving, this charge will experience electric force. So we need to say an electric charge always experience a force in an electric field, whether the charge is stationary or in motion.